You ask me to explain magnetism. How do magnets work? Why do they attract? And right away I have to stop you. Because magnets don't attract, not really, not in the way you think. They don't reach out and pull on each other. They don't have invisible arms. There's no force traveling through space grabbing on to the other magnet. That's not what's happening at all. What's happening is much stranger. And to understand it, you have to give up a lot of your intuitions about how the world works. You have to be willing to accept that what seems obvious isn't true. Let me start with the thing that bothers people most. When you hold two magnets near each other and you feel them pull together, what are you feeling? What's actually happening? Most people think there's a force. The magnets are exerting a force on each other through empty space, across the gap between them. One magnet reaches out and pulls on the other. But how? How does one magnet know the other is there? How does it reach across empty space? What's doing the reaching? And people say, it's the magnetic field, as if that explains it, as if naming it makes it clear. But what is a magnetic field? Is it a thing? Is it real? Is it physically there in the space between the magnets? Yes, it is. The field is real. It's not just a mathematical convenience. It's not just a way of calculating forces. It's an actual physical thing that exists in space. But here's where it gets strange. The field isn't reaching out from one magnet to the other. The field is everywhere. Both magnets are sitting in a field, and they're both responding to the field around them. They're not responding to each other. They're responding to the field. Okay, so what's a field? Well, let me try to explain it this way. You know what water is. You can put your hand in water. You can feel it. It's there. It's a substance. Now imagine space is filled with something. Not water, not air, but something. An electromagnetic field. And that field has properties. It has strength. It has direction. It can push and pull on charges, on electrons, on protons. A magnet is just a collection of aligned electrons. The electrons are spinning, and that spin creates a magnetic moment. And when you have trillions of these little magnetic moments, all lined up the same way, you get a macroscopic magnet. Now that magnet creates a field around it, or rather, it changes the field that was already there. Space is never empty. There's always a field. The magnet just changes the configuration of that field in its vicinity. And the other magnet sitting nearby, it's not feeling the first magnet, it's feeling the field. The field around it is distorted by the presence of the first magnet, and that distortion causes forces on the second magnet. So magnets don't attract each other. Magnets respond to the field around them, and the field around them has been modified by the presence of other magnets. It's subtle, but it's important. Now you want to know, what is this field made of? And here's what I have to tell you, something you won't like. We don't know. We can describe it mathematically. We can predict how it behaves. We can calculate what it will do in any situation. But we can't tell you what it's made of, because that question doesn't really make sense. The field is fundamental. It's not made of anything more basic. It's what the universe is made of. Matter, particles, all of that is just excitations in fields, disturbances in the underlying field. An electron isn't a little ball. It's a persistent disturbance in the electron field. A photon isn't a particle of light. It's an excitation in the electromagnetic field. And when two magnets interact, what's really happening is that the electromagnetic field is mediating the interaction. The field carries the force, not through space. The field is space in a sense. Or rather, space is filled with fields, and those fields are what allow forces to propagate. You can't have empty space with nothing in it, and then have forces acting across it. That doesn't make sense. The force has to be carried by something, and that something is the field. Now, if you want to go deeper to quantum mechanics, there's another way to think about it, and this is going to sound even stranger. In quantum field theory, we say that two magnets interact by exchanging virtual photons. Little packets of electromagnetic field that pop into existence, travel from one magnet to the other, and then disappear. These aren't real photons. You can't see them. You can't detect them directly. They violate energy conservation. But only for a very short time, so short that the uncertainty principle allows it. One magnet emits a virtual photon. That photon travels to the other magnet. That magnet absorbs it, and in that exchange, momentum is transferred. And that momentum transfer is what we perceive as a force. So the magnets aren't pulling on each other. They're throwing photons back and forth, virtual photons. And the exchange of these photons is what creates the appearance of attraction or repulsion. This is how all electromagnetic forces work, by the way, not just magnets. When you touch a table and you feel it solid under your hand, what you're feeling is electrons in your hand exchanging virtual photons with electrons in the table. Trillions upon trillions of virtual photons every second, and that exchange creates a repulsive force that prevents your hand from passing through. Everything that feels solid, everything that pushes or pulls electrically or magnetically, it's all virtual photons, all field interactions. But let's come back to magnets. You want to know, why do they attract or repel? Why do opposite poles attract and like poles repel? Well, the field has a direction. The magnetic field points from north to south. It has field lines. You've seen the diagrams. You put iron filings near a magnet and they line up along the field lines. Those field lines are real. They represent the direction of the field at each point in space. Now a magnet has a north pole and a south pole. The field comes out of the north pole and goes into the south pole. That's just how we define it. The field is looping around, coming out one end, curving around, going into the other end. When you bring two magnets near each other, the fields interact. If you put a north pole near a south pole, the fields line up. They reinforce each other. The field from one magnet flows smoothly into the other magnet. That's a lower energy configuration. The system wants to be in a lower energy state. So the magnets move together. We call that attraction. But if you put two north poles near each other, the fields push against each other. They're trying to go in opposite directions. The field lines bunch up and repel. That's a higher energy configuration. The magnets want to move apart to reduce that energy. We call that repulsion. But notice, the magnets aren't doing anything to each other. They're each responding to the total field around them. The field is doing all the work. Now, how strong is this field? How much force does it exert? Well, it depends on the magnets. Bigger magnets, stronger fields. Closer together, stronger force. It falls off with distance. The farther apart the magnets are, the weaker the interaction. But here's something interesting. The electromagnetic force is incredibly strong. Compared to gravity, it's about 10 to the 36 times stronger. That's a trillion times stronger. If you had two electrons sitting 1 meter apart, the electrical repulsion between them would be vastly stronger than the gravitational attraction. Gravity is incredibly weak. It only matters for very large objects like planets and stars, where you have huge amounts of mass all pulling together. For small things, for atoms and molecules, gravity is essentially irrelevant. Everything is electromagnetic. Chemistry is electromagnetic. Magnets are electromagnetic. The forces holding your body together are electromagnetic. You are held together by the exchange of virtual photons between the electrons and protons in your atoms. That's what keeps you from falling apart into a cloud of particles. That's what makes solid matter solid. Now here's the thing. I've been explaining this to you, but have I really explained it? I told you there's a field. Okay, what's a field? I told you it's a property of space. Fine, but what does that mean? I told you particles exchange virtual photons. Sure, but why? How? What are virtual photons really? And the truth is, I don't know. Nobody knows. We can describe what happens. We can calculate it. We can predict it with extraordinary accuracy. But we can't really explain it in terms of something simpler. Feynman himself said this. He gave a famous interview once where someone asked him to explain magnetism. And he went through several attempts and kept hitting the same problem. To explain magnetism, you have to use concepts that are just as mysterious as magnetism itself. You explain it with fields, but what are fields? You explain it with virtual photons, but what are those? You explain it with quantum mechanics, but quantum mechanics is more mysterious than magnetism. At some point, you have to accept that the universe just works this way. There are fundamental things that aren't made of anything simpler, things that just are. And the electromagnetic field is one of those things. We've learned how to work with it, how to calculate with it, how to predict what it will do. We can build motors and generators and magnets. We can use it to do useful work, but we can't reduce it to something more familiar. It's not like anything in everyday experience. It's just what it is. Okay, but let's look inside the magnet. What's making the field in the first place? Well, as I said, it's electrons. Electrons have a property called spin. Now, don't think of them as actually spinning. They're not little balls rotating. Spin is an intrinsic property, like charge. Electrons just have spin. It's part of what they are. And that spin creates a tiny magnetic field. Each electron is like a tiny bar magnet. It has a north pole and a south pole. In most materials, the electrons are all oriented randomly. Some spin this way, some spin that way. They cancel out. No net magnetic field. But in a magnet, in iron or nickel or cobalt, something special happens. The electrons can align. They all point the same way. And when billions and billions of electrons all align, you get a macroscopic magnetic field. Why do they align? Because it's energetically favorable. The electromagnetic force between the electrons wants them to line up. It's complicated. It involves quantum mechanics and the way electrons interact with each other. But the result is that in certain materials, you can get large regions called magnetic domains where all the electrons are aligned. And if you take a piece of iron and put it in a strong magnetic field, you can force all the domains to align the same way. And then you have a permanent magnet. Here's another question people ask. If the field extends out from the magnet in all directions, does it go on forever? Is the field infinite? Well, yes and no. The field doesn't stop at some specific distance. It keeps going. It gets weaker as you get farther away, but it never quite reaches zero. However, in practice, at some distance, it's so weak that you can't detect it anymore. It's drowned out by other fields. The Earth has a magnetic field. The Sun has a magnetic field. There are fields everywhere. So your little magnet's field becomes insignificant compared to everything else. But in principle, yes, the field extends infinitely. Every magnet in the universe is contributing a tiny bit to the field at every point in space. It's all interconnected. It's all one electromagnetic field, and everything that's charged or magnetic is part of it. You can't isolate a magnetic interaction. You can't have two magnets interacting in isolation with nothing else affecting them, because the field is everywhere and everything is part of the field. This is one of the weird things about fields. They're not localized. They're not confined to one place. They fill all of space, and they all interact with each other. It's a global phenomenon, not a local one. Another question: can you block a magnetic field? Like, can you put something between two magnets and stop them from attracting? Not really, not in the way you might think. You can redirect the field. If you put a piece of iron between two magnets, the field will flow through the iron instead of through the air. Iron is magnetic, so the field prefers to go through it. That can reduce the field in the air on the other side. But you're not blocking the field, you're just redirecting it. There's no such thing as a magnetic insulator, not like there is for electricity. With electricity, you can use rubber or plastic or glass, and the electric field doesn't penetrate. But with magnetism, the field goes through everything. It goes through your hand, through wood, through water, through anything. Some materials affect how the field is distributed, but nothing truly blocks it. Why? Because the magnetic field is a fundamental property of space. It's not something traveling through space that can be stopped. It's the space itself, in a sense. Or rather, it's a property of the field that fills space, and you can't wall off space. So let's come back to where we started. Magnets don't attract, not in the sense of reaching out and pulling on each other. What happens is this: a magnet creates a field around itself. That field extends out into space, modifying the electromagnetic field everywhere nearby. Another magnet, sitting in that modified field, responds to the field. The field exerts forces on the electrons in the second magnet, causing it to move. From the outside, it looks like the magnets are attracting, but really each magnet is just responding to the field around it. And the field around it has been modified by the presence of the other magnet. At the quantum level, you can think of it as an exchange of virtual photons. The magnets are constantly emitting and absorbing photons that don't quite exist. And in that exchange, momentum is transferred, creating what we perceive as a force. But here's the thing: this isn't just magnets. This is how all forces work. Gravity, electromagnetism, the nuclear forces, everything. Forces aren't things that travel through space. Forces are mediated by fields, by particles, by the structure of space-time itself. When you push on a wall, you're not directly touching the wall. You're exchanging virtual photons with the electrons in the wall. There's always a gap. Atoms never touch. Fields interact. That's all. And magnets are just a particularly obvious example of this, because we can feel the force at a distance. We can hold two magnets apart and feel them pulling. And it seems mysterious. How can they affect each other without touching? But they're not affecting each other. They're both affecting the field, and the field is affecting both of them. So why can't I explain magnets simply? Why can't I just say, magnets attract because of such and such, and have it make sense? Because at the bottom of it, we're dealing with something fundamental, something that isn't made of anything simpler. The electromagnetic field is just part of how the universe works. It's not like a mechanism we can take apart and understand. It's one of the basic building blocks. We can describe it, we can work with it, we can use it, but we can't reduce it to everyday experience. Because everyday experience is built on top of it. Everything you see and touch and feel is the result of electromagnetic fields interacting. You can't explain the foundation in terms of the things built on top of it. Magnets don't attract. They respond to fields. Fields mediated by virtual photons. Fields that are fundamental properties of space. Fields that we can calculate but not fully visualize. And maybe that's unsatisfying. Maybe you wanted a simple answer. But that's not how nature works. Nature is what it is. And our job isn't to make it familiar. Our job is to describe it accurately, to predict it, to work with it. And that's what we've done with electromagnetism. We figured out the rules. We can calculate anything you want. We just can't make it simple, because it isn't simple. It's the foundation, and foundations don't simplify. That's magnetism, not attraction, field interaction, virtual photon exchange, quantum electromagnetic phenomena, strange, precise, fundamental, and utterly unlike what you thought.